Yeah, okay, yeah, you can go ahead. Thank you.
Okay, so we were just talking about the last couple of lectures, and the point was made by Juan that something of interest would be to look at some of the more open questions in game theory and the dynamics of games, which is very convenient because that's exactly what we're going to be talking about today. Because over the last couple of talks, we've looked more at like a framework for game theory, trying to understand how it works, but specifically in the context of two-player games. So these bi-matrix games, right? Where you have two players and their payoffs are encoded by these matrices. But what you were interested in, what I too am interested in, is what happens when we start to move beyond this simplistic assumption of two players, right? What happens when we start to couple maybe 3, 4, n players together in a game? And we're going to be looking at that from two perspectives. Now, I say today we're going to be focusing on the first one, the network games, right? In which essentially the idea is we take this population and we impose a structure on it so that not everyone is interacting with everyone, but rather, let's say we have like a social media network, or maybe just through family and friends, people are interacting to who they are connected with, and those people then interact with their friends and family, etc., right? So we've imposed some kind of structure on the interaction in this population. The second way that we want to look at populations is through what's called a mean field game. In the mean field game, essentially the idea is that instead of looking, well, what we do is we take the number of agents and we extend it all the way out to infinity, right? And what that allows us to do, what that assumption allows us to do, is instead of looking at the microstate of the system, so looking at each agent's individual state, we rather model a distribution over the entire population, and now each agent only has to react to this distribution function, right? But as I said, we're going to focus on the network game today and then go on to the mean field game later on. Okay, so network games. To define what a network game is, let's just quickly recap what a game was, right? So a game, if you guys remember, was a set of agents coupled with the actions that they can take, right? So what they can do, and a payoff function, which essentially encodes why they choose the actions that they end up choosing, right? Because we're trying to take the actions that maximize our payoff. Okay. Now, what's specific about a network game, as I said earlier, is how the agents interact with one another. So that, for example, if I have, my purple agent, then my purple agent isn't interacting with everyone. It's only interacting with its 5 blue neighbors, right? So if we call that 1, it's only interacting with 2, 3, 4, 5, and 6, right? It's not interacting with 7. Now, to formalize this again, we've got to impose this network, this underlying graph that depicts how everyone communicates with one another, right? And to do that, we have this, what's called an interaction graph. I'm just going to abbreviate that for a second. And in the graph, most of you, I'm sure, will have looked at graph theory before in the context of, Bayesian reasoning or discrete algorithms or something like that. But just as a quick recap, in a graph, we have a few elements. We have the nodes, which in the game just corresponds to the agents, right? We have an edge set, which is essentially just all the pairs of agents ij who are connected to one another, right? So 1 and 2 are connected to one another, et cetera, et cetera. And finally, we have a weighted adjacency matrix, right? And what this essentially encodes is a matrix with zeros along all elements where the agents aren't connected to one another, right? So if I and j are not connected, right? So if I and j are not connected, then wij is going to equal 0. If they are connected, then it's going to equal some positive number, right? Now, what this weight allows us to do, essentially, is if we just impose it across these edges, then what it says is it gives us a measure of priority of the information between two agents, right? So if in this example, if W12 is bigger than W13, then that means agent 1 is preferring the information or prioritizing the information from agent 2 over agent 3, right? For the most part though, in most studies, all of these weights are just taken to equal 1 so that everyone just has a equal weighting. We don't have to worry about prioritization at all. But that's not a necessary assumption. In the last talk, we looked at the action of fictitious play in a specific type of network game, the network aggregative game, right? And in that one, we didn't make this assumption of all the weights equaling 1. We could have the weights equal whatever we want. But for the purposes of this talk, we are going to make that restriction. And we're going to focus on just the unweighted problem. We're also going to make one more restriction. Instead of looking at this huge population, right, we're going to focus our attention on just one of these cliques. All right, so just one of these, one of the subset of just 3 nodes. And the reason why we're going to do that is because we have an understanding of bimatrix games. We've been looking at that for the last 2 talks. And so a natural extension is, okay, well, let's just put one more person into it. Let's turn the 2-body problem into a 3-body problem, right? We already know that in gravitation, for example, turning into, moving from the 2-body to the 3-body problem is not a trivial task. And so we'd like to do a similar thing with games. So let's have a look at this particular 3-body problem, right? There's 2 examples here where we have 3 agents in the network. And the first is what's called a ZZZ game, for pretty obvious reasons, where essentially along each of the edges of this network, the agent is engaged in a zero-sum game, right? But a different zero-sum game along, or not necessarily, but could be a different zero-sum game along each of the edges, right? And on the other hand, we have what's called a CCC game, where the agents are engaged in a purely cooperative problem, right? Now, we're going to make one more restriction. The restriction that we're going to make is we're going to focus that on each of these bimatrix games along the edges, we're going to impose that they're all 2-action games. Okay, the reason why we're going to focus on 2-action games is because we already have a pretty solid understanding of each of our learning algorithms on these 2x2 games, so these 2-player 2-action games, right? We know that, for example, Replicator, instead of drawing it, I can just show you. Replicator gave rise to these cycles, right? That is not the right thing. It gave rise to these cycles where the trajectories just kept cycling around the equilibrium, right? This was for a zero-sum game, mind you. Now, for a coordination game, the behavior, we didn't look at it specifically unless you think about the Prisoner's Dilemma game, in which essentially what happened is the agents ended up converging down to one of the pure strategies, right? It could be a different pure strategy depending on which initial condition you start at. But for example, you know, if in the Prisoner's Dilemma, if one agent confesses, it is beneficial for the other agent to also confess, right? So when we applied a replicator on it, we got to this stage where both agents were confessing in the end, right? And so now that we have this understanding of what replicator is going to do in a 2-player game, let's see what happens when we couple them together, right? So the way that this coupling works is that each agent has to choose the same action in each of the games that it's playing with both of its neighbors, right? But it could be playing a different game against either neighbor. I hope that makes sense. Yeah, so let's have a look at what happens when we apply replicate. Yes.
One question. how big is the set of games that you play? For example, how close could they be?
Close in what sense? Sorry.
In the sense that maybe you have a kind of open dense set of games that you play, and maybe in one edge, you may be playing a game that is quite close in some kind of topological sense to the games we're playing on the other edge.
Okay, that's actually a really good point from the perspective of analysis of these sorts of games. And the reason I can't answer that is because this work that we're about to look into is pretty uncharted waters, in the sense that most of the results that we're looking at come from simulation and simulation alone, as opposed to analysis. So the point of developing a general theory for these sorts of three-player networks, in terms of what kind of games are allowed and what kind of behaviors do different combinations of games give, completely open question, has not been analyzed at all. So what I'm going to be showing you is very representative, but the analysis for it is very much open for hopefully your discovery as well.
Okay.
So that's kind of a non-answer to your question, but I hope it suffices.
Yes, thanks.
Okay, so first representative example for this these sets of games. On the left, we have the ZZZ, so the purely zero sum, and on the right, the purely coordination. Now, what's interesting to see here is that the same behavior that we saw in the bimatrix game, right? So for example, in the zero sum bimatrix game, where was it? Here, we saw these cycles, right? Same cycles are going to appear when we couple them together. It's kind of strange because it's not always going to be the case that you take two systems independently, couple them together, and it's going to achieve the exact same set of dynamics. But in this case, it does, right? And the same holds true for the coordination game, where before we had these, corner convergence, corner equilibria, sorry, and the same behavior occurs for the three-body problem, right? Now, that in some sense is kind of boring because it means that we can just extend our analysis. And in fact, the analysis works in exactly the same way. This is the bit where the analysis actually does work. And in particular, if we look at the ZZZ game, the purely zero-sum game, something interesting happens because we've already seen cycles in two-player zero-sum games, right? You could think of a two-player game as a two-player network game, right? There's just one connection. You don't necessarily need the connection there, but we can imagine that it's a two-player network. We've seen it in a three-player network. The same cycles occur when we have the zero-sum assumption. So question to ask naturally will be, if we always have this zero-sum assumption in place, are we going to get cyclic behavior, right? Now, this was actually answered positively in 2017, I believe. Yes, 2017, in which the authors essentially applied this result of what's called Poincare recurrence. This is a pretty seminal result in dynamical systems, which essentially says that if we take any open set, right, and we look at the trajectories that pass through it, the trajectories can do whatever they want outside, right? But eventually they will cross that open set again, and they will do so infinitely often, right? So what that tells us is that we can take our initial conditions and the trajectory of replicator or the dynamical system that we're looking at in particular, if it's recurrent, that means that we're going to keep coming back to the initial condition or arbitrarily close to that, right? And in fact, we can show that this result is positive for replicator as well, because what the authors were able to do is show that it satisfies both conditions that are required. So volume preservation and that the orbits are bounded. Now, the first part of that, the volume preservation, we've already looked at. We've already seen this because we looked at replicator in zero-sum games, and we showed that it was a Hamiltonian system, right? So it conserves a notion of energy along the trajectory. And what that tells us is that the system is conservative, right? Now, in particular, we use the word, where did we use the word? Volume preserving. And what that essentially means is that if I take a set of initial conditions and I follow it along in its trajectory through a replicator, the set of initial conditions can end up looking something like really weird, but the volume of both of these sets will always remain constant. Okay, that's the idea of volume preservation. And it turns out that Hamiltonian systems always preserve volume, right? So this first part of the problem is already solved. The bit about bounded orbits is a little bit more technical, but combined, when you combine those two results together and show that they hold true for the replicator dynamics, you can say immediately that it satisfies the conditions for Poincare recurrence, right? And that tells us that in zero-sum games or in these zero-sum networks, replicator is always going to have this recurrent behavior. You're not going to go down to an equilibrium at any point, right? Unless, of course, you start at the equilibrium to begin with. But other than that, you're always going to end up cycling around, which is what we've seen experimentally. And this is one of the ones that we can actually show analytically as well, right? Any questions just based off that? No, okay. By the way, I can't see the chat. So if there are any in the chat, then please feel free to interrupt me.
Yeah, no, there are no questions here.
Okay, so we've seen non-recurrent behavior in zero-sum games, convergent behavior in coordination games. The follow-up question is, let's try and mix these together, right? So that we have what are called CCZ and ZZC for, again, pretty obvious reasons. Essentially, now we have the situation in which not everyone interacts with everyone in the exact same way, right? So I might be in coordination with one of my opponents, I might be competing against another, right? And you might have a different relationship with those neighbors as well. And so we're really starting to mix it up here. And our question again is, okay, what kind of behavior do we want to get? Now, here we're really getting into the whole open question region, because most of what we'll be looking at here, in fact, pretty much all of what we're going to be looking at here is based on experiment. The analysis and developing a general theory for the behavior of not only replicator, but of all of the dynamics is still very much an open question. Okay, so let's have a look at the first one, the CCZ game and the ZZC game, right? Again, for replicator. What we end up seeing is quite interesting dynamics. And again, these are completely representative. I'm just showing you a few games. Of course, if you play other games, the dynamics are going to be different. This is all just representative of the sort of behavior that you expect to see. And what you end up seeing is that in the, which one was the CCZ game and the ZZC game, the cyclic behavior that comes from the zero-sum game is maintained, right? However, there is a cooperative element that tries to push the whole system towards an equilibrium. And so you get this interesting combination of the two, where, for example, in this particular, in the CCZ game, we have that one of the agents, the one who's engaged in coordination with both of its opponents, right? That agent's behavior stays fixed, right? So it ends up converging. Whereas the other two who are engaged in a zero-sum game with one another just keep cycling, right? And so you've kind of coupled these dynamics together a little bit. And the same thing happens when you use a ZZC game, where the recurrent behavior remains for the most part, but there is an element that's trying to push the system towards a corner convergence. Now, again, as I said, this is representative of the sort of thing you would expect, but I'm really hoping that soon as we progress, this open question of, evolutionary dynamics is pretty well understood in biomatrix games. It's been studied for 40 plus years. So there are obviously gaps in that theory, but for the most part, it's understood. Not so much when you introduce the three-body problem. The stuff that I've just shown you so far was all done in 2018. And whilst there's analysis in there, a lot of it is also quite experimental. And so developing this general theory for evolutionary dynamics in the three-body case, very much open for discovery. Anyway, so that's the behavior of evolutionary dynamics. We have two other dynamics that we would like to look at, fictitious play and Q-learning, the ones that we've loved so dearly over the past couple of talks. But before we do that, are there any questions based on what we've just talked about? Okay. So when we move on to fictitious play, there's one thing that I want to pose just before we look at the results for three-body type problems. And the result, which is pretty remarkable, is this one from Miyazawa, which I think is not too recent. I think it was done about 30 years ago. But what it says is that fictitious play is going to converge in all two-player two-action games, right? So that's what the 2x2 means, the two-player two-action games, okay? And this is regardless of the type of game played. So it could be coordination, it could be zero-sum, it doesn't matter. Fictitious play is always going to converge when you have a 2x2 game, yeah? And we saw that in the last talk when we were looking at fictitious play, because the same matching pennies game, which gave us the cyclic dynamics and replicator, we saw spiral convergence in fictitious play, right? Convergence down to an equilibrium in the center. And so our question now is, okay, well, if we know everything is going to converge when the games are uncoupled, what happens when the games are coupled, right? What happens when we start to mix in these, mix these games in together? So let's start with the zero sum and the coordination. And as you'd expect, what we end up seeing, and this is true of all the experiments I've run, is that the behavior that you would expect in the two-player case. So for example, when we run the matching pennies game, on the two-player case, we got this spiral convergence. In the three-body case, right, where replicator gave these cycles, fictitious play continues to give these spirals down to the center, which suggests that the analysis should extend pretty naturally. And actually, again, for zero-sum games, this is the part that has been done. The analysis has been done for this bit. In fact, it was shown in very recently, actually, in 2020, that that fictitious play in these zero-sum networks is going to converge to a Nash equilibrium. Okay, and similarly for the coordination game, we get the corner convergence, the same thing that we'd expect generally. And again, this purely coordination game is a little bit trivial, just because all agents are trying to accomplish the same thing, really. So if one action is promoted, every other agent should promote that action as well. And so that one's a little bit less interesting. But what is more interesting is the mixed cases, right? Where we start to mix zero-sum and coordination games together. Again, throughout the experiments that I've seen, we seem to see that fictitious play is always converging. So if we have a look at which one was this? This was the CCZ game, and this is the ZZC game. ZZC converges down to an equilibrium, nice and simple. But if we remember back to Replicator, we saw that the agents move towards the zero-sum component and then just cycle around as you'd expect, right? Whereas fictitious play does the exact same motion back to the zero-sum plane, if you will. But as you'd expect, we end up spiraling down towards a fixed point along the way, right? Because this time fictitious play in a zero-sum game is actually going to converge. And so what we've seen so far is fictitious play seems to converge in pretty much everything we throw at it, right? And so we have this question of, well, is that going to be true of all 3-player networks? Or are there going to be some 3-player networks in which fictitious play doesn't converge? You know, so for example, in the case of 2-player games, it was thought that fictitious play was a natural way to reach a Nash equilibrium. We're always going to reach it, right up until Lloyd Shapley gave us the Shapley game, in which it was shown that fictitious play doesn't converge in this game. Is there something similar going on here? Is there a similar type of game that we can find for which fictitious play isn't going to converge? Turns out the answer is yes, as you might expect from my little motivation there. And the particular type of game that I want to show you is the mismatching pennies game. Okay, this is a very particular example in which instead of having these undirected graphs that we've seen so far, we have a directed cyclic graph, right? In which each agent is going to respond to the behavior of the previous agent. So 1 is going to respond to the behavior of 3, 2 is going to respond to the behavior of 1, etc. Right? And in particular, what the payoff matrix is telling us is that each agent wants to choose a different action to the previous agent, right? So these off diagonals suggest that both agents are choosing a different action, right? So that if we choose either this action or this action, then agent I ends up winning. But if we choose the actions on the diagonal so that I and I minus 1 are both playing the same action, then our player ends up losing out, right? So all agents are trying to be different to the previous agent, but they all have to play the exact same action in the game. I hope that makes sense, right? So this is you might think this is quite a contrived example that I might have just pulled it out of nowhere. However, the reason why we're looking at it is for historical reasons. In fact, this was the first algorithm, or the first game, sorry, for which it was shown that Replicator in these 3-body situations doesn't converge, right? So it was shown in 2014. So again, really not that long ago, that the Replicator dynamic, instead of converging down to an equilibrium, as long as you start away from the equilibrium, you'll end up converging to these cycles. It's a little bit hard to see in this angle, but they cycle basically really, really close to the boundary of the simplex, and they keep cycling and they never equilibrate, okay? And so this is one of the first examples of a 3-body problem that Replicator couldn't solve. And so a natural question to ask is, well, fictitious play has been able to solve everything that Replicator has so far, so maybe it can solve this one too, right? Turns out that's not the case. If we apply fictitious play on the mismatching pennies game, it achieves a limit cycle in exactly the same way that Replicator does. In fact, just based off the experiments, it seems to be that there's some form of annulus that exists. Again, this is just based off experiment, that interior points are attracted towards this Nash equilibrium in the center, whereas the initial conditions outside of that reach this limit cycle, right? So in exactly the same way that the Shapley family suggests that, we're not always going to get convergence for bimatrix games, the mismatching pennies example seems to show that we're not going to get convergence for fictitious play in all of these three-body games. Now, with that said, everything that we've looked at regarding fictitious play is completely experimental. The question of the behavior of fictitious play in these sorts of networks, other than the purely zero-sum game, which I mentioned had already been solved in 2020. So this result from 2020 showed that for these zero-sum networks, fictitious play is always going to converge. So we've got that one down. But everything else, every other possible game that isn't necessarily zero-sum, is still very much open for discovery. And hopefully a theory for that can be developed in the coming years. Okay, so fictitious play, and replicator, I've just given away what we're doing next. Q-learning is the last one that we need to look at. And in many ways, I personally think it's the most interesting of the lot. The reason why I think it's the most interesting of the lot is because Q-learning is very similar to replicator. Right? Except if you remember from the last talk, Q-learning has this added entropic term, which essentially encodes the desire for agents to explore their strategy space as opposed to just exploiting the best performing actions, right? So in some sense, our agents aren't completely irrational, as replicator implies, but sometimes like to try something different to see what works better, right? And the effect of that that entropic term, or that exploration, was that the dynamics, instead of where replicator would reach these cycles and was conservative, we found that Q-learning was dissipative and converges down to an equilibrium in all 2x2 games. Same as fictitious play, 2x2 games with Q-learning is completely solved, right? But now we have to ask what happens in our three-body problems. So instead of showing you the really obvious ones, the ZZZ and the coordination games, let's skip past those because those are trivial and we end up seeing convergence. We'll instead look directly at the mixed games, right? Which, in the same way as fictitious play, seems to show convergence with Q-learning, right? Regardless of our initial conditions, we end up in the, I think this was, yeah, sorry, this was the CCZ and this is the ZZZ game, right? We end up seeing convergence down. Now, once we've established this, and once we've run it for a number of experiments, which we have, and seen convergence in pretty much all games, we need to ask, okay, what about this mismatching pennies game? That has seemed to baffle both replicator and fictitious play. What about Q-learning? Is there some glimmer of hope? As it turns out, there is. But here's the thing, Q-learning, if you guys remember, was dependent on these two parameters, alpha and tau. Tau essentially encoding the like a measure of irrationality, or a measure of how much the agent wants to explore their actions, right? Whereas alpha was a step length. And the behavior of Q-learning is, of course, going to depend on how you choose these parameters, right? So what we do is we look at Q-learning for on this mismatching pennies game for different values of alpha and tau. And what ends up being seen is as you vary tau, specifically tau, you end up moving from something that was initially convergent, right? So we took the mismatching pennies game, which was completely convergent to begin with, and we start increasing tau. Now, if you notice in the equation, this tau parameter, if you increase it, what you're doing is you're increasing the contribution of this replicator part type of the term, right? And eventually this replicator part is going to end up dominating over the entropic term, right? So as you increase tau, you're getting more and more replicator-like, so to speak. And so as you increase your value, you end up seeing that you converge to this limit cycle instead of a fixed point in the same way that replicator does. And as you keep increasing it, you'll eventually get to the same limit cycle that replicator showed earlier. And so you can see that there's this bifurcation that occurs. Essentially, if you go back the other direction, you're moving from a limit cycle, eventually reaching a fixed point, right? As you vary the value of tau. And so there's a question of, is there always going to be a choice of parameters for which this behavior occurs? Is there always going to be a choice of alpha or tau for which you move from non-convergent replicator-like behavior to convergent behavior in Q-learning? And that, again, is a completely open question, one that we're looking at the moment, and hopefully we'll make some progress on that. But all of this is to say that the problem of every single one of these dynamics in populations of more than 2 agents is open and available for exploration. And hopefully over the next few years, we'll start to see a theory developing on those as well. Thank you. Are there any questions based on what we've talked about today?
Yes, I have a small question.
Yeah.
At one point of your talk, you mentioned kind of synchronization in the playing of the games.
Yeah.
I mean, when one player plays an action, does it mean that all the other players instantaneously play their corresponding actions, or could there be some delay in one of them?
So there are different types of games that you'd be referring to here. There's the synchronous game and the asynchronous game, right? What we've been looking at so far is the synchronous problem, in which all of the agents change their behavior simultaneously. The asynchronous one is one that is quite unexplored. I'm actually not sure why. There are a few asynchronous games, for example, like leader-follower type systems, which have some basis behind them, but not as much as what we've been looking at so far. So to answer your question, everything that we've looked at so far is the synchronous case, where everyone's changing their action at the same time. But the results for the asynchronous corollary are pretty open for exploration.
Okay, thanks.
All right. Are you done, Aamal?
Yep.
Ah, okay, nice. Okay, good. Any other questions? All right. Are you still okay for next one, Monday at 12?
I am, yeah.
Yeah, all right. Okay, so that would be the last session, right?
Okay.
Okay, okay. Okay, thank you very much. Yeah.
Thank you, everyone.
Okay, thanks, everyone. Thanks, take care. Thanks, bye-bye. Bye.